I will now introduce you to the ML4Floods project. ML4Floods is an end-to-end pipeline for flood extent estimation. The practical case study has two notebooks. One notebook shows you how you can train a convolutional neural network for flood extent segmentation. And the second notebook shows you then the inference process, how you can apply the pre-trained model onto a Sentinel-2 image in order to classify floods. The practical workflow also makes use of a benchmark dataset, which is called WorldFloods. And WorldFloods is a benchmark dataset that contains of 422 flood extent maps, which have been created based on flood events that occurred between November 2015 and March 2019. And with this, I propose that we start with the first notebook with the training process to train a flood extent segmentation model based on the WorldFloods benchmark dataset. So we are in week 6, where we introduce you to machine learning and climate applications. And the case study we show you now is the ML4Floods case study, which is under the topic number 6F. And if you go to this folder, you see 3 different notebooks, one related to functions, then one related to training, and the other one is introducing you to the inference process of the pre-trained model. And then you also see 3 folders, one containing the WorldFloods benchmark dataset, then another folder contains some TIFFs images, so pre-processed Sentinel-2 images for the inference process, and another folder which contains already pre-trained models for training purposes. And this video is about the training process. So we opened the notebook related to the training. This notebook introduces you to the ML4Floods project, which is a project that developed an end-to-end machine learning pipeline for flood extent estimation. So ML4Floods is in fact a Python package that offers you functions related to data pre-processing, model training, model deployment, and also model evaluation and visualization. And so this workflow shows you how you can train a flood extent segmentation model based on the WorldFloods benchmark dataset in order to produce flood masks and flood classifications. The workflow trains a convolutional neural network based on the WorldFloods benchmark dataset, and the aimed output are Sentinel-2 images classified in one of 3 classes, either land, water and flood, and clouds. And we also provided you here additional links to the Machine Learning for Floods GitHub repository. There's also a paper about the project, and there's also based on the GitHub repository, a Machine Learning for Floods book, or online book, which has a lot of resources about the project itself and also additional information. And with this, we start as we always start. We load a set of required libraries for the workflow. As I said, we make use of the ML4Floods Python package. So this is the Python package that is one result of the ML4Floods project. And here we load quite a few functions related to data pre-processing, model deployment, model training, but also evaluating the model performance. The first step is to load a configuration file from the ML4Floods Python package, and we can use the library pkj_resources to retrieve the file path to the configuration file. And the configuration file has the name WorldFloods_template. So this is one template the Machine Learning for Floods project offers. And this can be already found in the folder models and then configurations. And the machine learning for floods function get_default_config loads then the final configuration file. And if we load it, you see that in principle it's a Python dictionary consisting of different data and model parameters that are required for deploying the model and also training the model and preparing the data. So as a note, this workflow makes use of the ML4Floods Python package, and in the training environment this package is already installed, but we provide you here also the command in case you want to replicate it on your local machine. We provide you the command how you can also install this package on your local machine. And this is what we do here. So we load the configuration file, and we see then this configuration file lists a set of data parameters required to prepare the data, and also some model parameters and specifically also hyperparameters. And the next step is then to override the default folder where to store the experiments. So the default folder is worldfloods_demo_test, but we want to set it to the folder path training_demo. And this is what we do here. So from the config file, we select experiment name and we overwrite it to a different folder name. And then before we also start with the data pre-processing, we would like to set a random number generator that can help us also to reproduce results, and we just use the random number that is set in the configuration file, which is set to 12 here. The next step is optional. This is just to show you how you can download data and also inspect the training data. So this helps you to reproduce it also on your local machine. But there is the step in downloading data has already been done. So the data is already part of the training platform here. But additionally, we also inspect the training data that you get a better feeling on the World Floods benchmark data set, what it actually contains. So downloading the data from the World Floods data set can be done with the ML4Floods Python package. If you want to reproduce what we already done, so this step has already been executed, you have to override a set of data parameters that are part of the configuration file. And this is what we do here. So we overrode the batch size, which is a control parameter and should be set depending on the space on your machine. Then the loader type, which can be local, so this means then the images are available locally, or it can be bucket, which loads the images directly from a Google Cloud Storage bucket. Then the number of workers, so in the training platform this is set to 0 because we don't have machines that allow parallel processing. And the path to split, which is a local folder to store the data. So this is also what we set here to the folder which is available in the training folder here, worldfloods_v1_sample. And this is important. So we set the parameter train_test_split_file to a train test split sample, because the full World Floods data set is 264 gigabytes. But for training purposes and for this example specifically, you can use this JSON file, which only downloads a subset of the training, validation and test data sets. And this subset has a volume of 13 gigabytes. And with the download key in the configuration file, you can specify which data types shall be downloaded. So there are also these 3 training subsets available. So one for training, one for validation, and one for testing. And in this case, we download the 2 subsets, one for training and one for validation. And once the arguments above have been specified, we can then continue and download the data set with the help of the function get_dataset. And this is what we do here. So we say download the data set if it's not available yet, based on the data parameters we just defined in the configuration file. And so this is what this step is doing, and then the next step is we can inspect what actually has been downloaded. So the data set we define here is a PyTorch Lightning data module object, and this object contains the WorldFloods training and validation data sets as attributes. So we have the attributes dataset.train_dataset and dataset.val_dataset. And we can load these different subsets and also inspect the dimensions or the number of items of the respective subset. And we see that we have 6,298 items for training and 1,284 items for validation. The next step is then to load a specific data set by creating a PyTorch data loader object, which applies the functions train_data loader and val_data loader. And so the code below creates first a PyTorch data loader object for the training data set, and then selects a random batch or a random list or number of items of the data set, depending on the batch size that was defined in the configuration file. And each item consists of 2 items, images and a mask item. And if we check the dimensions of these 2 items, we see that the image item has 4 dimensions, so we have 16 items because we defined the batch size 16 in the configuration file. 13, that stands for the number of bands of a Sentinel-2 image file, and 256 times 256 represents the number of columns and rows per image. And the mask has also 4 dimensions, so it has 16 images, but only 1 item with the classified labels of flood, cloud or land pixels, but the same number of columns and the same number of rows. And this is what we do here. So we create a PyTorch data loader object, and we then inspect the shape of the image and mask items. And now we are in a state that we can inspect some of the training images, and we can inspect this with the function plot_batch from the WorldFloods module. And the function plots a given number. So in the case below, we give the number 6. So a given number of columns. So we have 6 different columns. And below we also see 3 rows. The first row shows 6 training images as true color composites. The second row shows 6 training images as false color composites, highlighting specifically water. And the third row shows the land, water, cloud masks of the respective images. And this is what we see here. We have a set of different images as part of the WorldFloods benchmark data set in true color, in false color, and then also the flood and cloud and land water mask. So now we loaded some data from the WorldFloods benchmark data set, and we also inspected how the data looks like and what the WorldFloods benchmark data set contains. And the next step is then to set up the convolutional neural network model. We can set up the convolutional neural network model with the configuration file as well, because the configuration file contains a section called model params, and this is a group of parameters relevant for setting up and training the model. And if we print this here, we see that we already have a set of parameters set. So we have a set of hyperparameters, which includes maximum tull size, metric monitor, channel configuration, label names, which contains our 3 classes, land, water, and cloud, number of classes, maximum number of epochs, etc. And we want to change a set of parameters which we list here. So we want to change the model folder, and in order to specify a local folder name, we want to change the parameter test, and we want to set it to false because we are now in the training process and we want to train a model from scratch. So we don't want to test a pre-trained model. Then we set train to true, which specifies that we want to train a model from scratch. And we also set the hyperparameters model type to simple CNN, which trains a simple convolutional neural network. But there is also other options available. So, so you can specify between a simple convolutional neural network, a UNet, or a linear algorithm. And the hyperparameter maximum epoch sets the number of training cycles, so the number of epochs, so the number of how often the model is trained and validated against the validation data. And we set this number to 4. And additionally, for training and also being on the training platform, we set the GPU's parameter to none because the training platform does not offer any GPU computing support. But if you have an environment that offers GPU support, then you can skip this step, and you can also make use of a GPU calculations or computing. So the next step is to get the model. So the function get_model allows you to load a pre-configured convolutional neural network architecture. And in the configuration file, we specified simple CNN, which is a sequential model with the following layer architecture. So the layer architecture has 4 convolutional layers with each a ReLU activation in between, and the final convolution layer that converts 128 bands to the final 3 classes we want to classify: cloud, water, and land. There are alternative architectures available as part of the ML4Floods library, and alternatively you can also load a UNet or linear model architecture. And this is what we do here. So we load the model we want to use, or the model architecture we want to use for training. And here's an optional step in order to fine-tune the model. So training the model from scratch takes quite a long time. Instead, we could also load the weights of a pre-trained model and only fine-tune the model with the data we load specifically here. So with the training data we loaded. And for this, it is enough also to train the model with only a very few epochs. And this is what we do here. So we specify the pre-trained model that is available on a Google Cloud Storage bucket, and with the function load_state_dictionary, we load weights of a predefined model. And then the next step is to set up some lightning callbacks. So callbacks are implementations that help us to better understand the behavior during the training process. And so one callback that is used quite often is, for example, model checkpoint, which saves the best performing model checkpoint to the locally defined folder. Or early stopping, which means that if the training process does not improve after a set number of cycles, then, so in this case, after 10 epochs, then the model training stops. So we have an early stopping, and then the best model checkpoint is the best model or the best performing model. And this is what we define here. So we define the experiment path, and we define the model checkpoint and the early stop callbacks. So now we defined the model architecture we want to use to pre-train the model, and the next step would then be the training process or the fitting process. So to fit the model onto the training data we loaded at the beginning. This is an optional step in this workflow because the training of the model takes quite a long time, and so we provide you the code and the example to see how you can train or fit the model onto the training data, but you can also skip this step and go directly to the evaluation of the model performance, where we load a pre-trained model of the ML4Floods project. So if you want to train the model for model training, we can make use of the PyTorch Lightning Trainer, which is an abstraction that automates the training of the model. And so this is something specific for the PyTorch library. And the first step is to define the PyTorch trainer, which in principle configures the parameters that are required for training. And you can provide a trainer the defined callbacks, which we just defined, and also some of the hyperparameters of the configuration file. And this is what we do here. So this is the trainer object, and we define a set of parameters that are required for the training process. And once the trainer is defined, we can use the trainer and we can use the function fit in order to fit or train the model. And this is what's happening here, but we don't execute this step because the training process takes quite a long time. Instead, we go directly to the next step in order to show you how you can evaluate a model performance. And for this, we already load a pre-trained model that is part of the ML4Floods library or ML4Floods project. So we skipped the training process and we go directly to the model evaluation. And in this part, we load a pre-trained model that is part of the ML4Floods project in order to show you how you can evaluate the model performance. So the first step is to load the pre-trained model, and we can load the weights of a pre-trained model from the ML4Floods package with the function load_state_dictionary. And this is what we do here. So we specify the model with the experiment number WFV1_SCNN20. We define the model and then we apply the function and we load the pre-trained weights. And this is what we do here. So we apply the function load_state_dictionary and we load the weights of a pre-trained model. So a machine learning model provides logits as output, and logits are non-normalized predictions of the model. And so in multi-class classification problems, logits usually are in the input for the softmax function, which converts logits to pixel-wise probabilities. And we can load the logits directly from the loaded model. And in the code below, we load these logits of 16 randomly selected images. And this is what we do here. So we first load the logits from the pre-trained model, and then we print the shape of these logits, which are non-normalized predictions of the model. And we see here that we have 16 randomly selected images because we set the batch size 16. We have 3 classes because we want to classify the image in 3 classes, and we have 256 rows and columns. And the next step is then to convert the logits into probabilities. And we can do this in PyTorch with the function softmax, which converts the logits into probabilities, where each image has 3 channels. And the function softmax from PyTorch converts the logits into probabilities, where each image will have a probability for each of the 3 classes. So for the class land, water, and cloud. And the sum of the probabilities of all classes sums to 1. And the final classification or the final class of the specific pixel is the class with the highest probability. And we can choose the final predicted class with the function argmax from the NumPy image. And as a result, the shape of the prediction object decreases from 16 images with 3 channels to only 16 images to only 1 value, which we are interested in because each pixel should have been classified into one final class. And this is what we do here. So we convert the logits into probabilities and then we select the highest probability for each pixel. Now we can plot again a set of 6 images which showcases the input images from the world floods, benchmark data set in true color, in false color, also the mask, and at the same time also the predictions. And this is what we see here. So we see again 6 columns which showcases 6 different images and 4 different rows showing first the true color composite, secondly the false color composite, third the land, water, cloud mask of each image, and fourth the predictions of the land, water, cloud classes. And this is what we see here. So these are the predictions that the pre-trained model did based on the input data. And so now the next step is to compute some performance metrics that help you to better assess the accuracy of the model. And we can use the function compute_metrics from the ML4Floods package. And this function computes 3 common performance metrics. The first is the confusion matrix, which is a table that describes the performance of a classification model on a set of test data. Then the precision recall curve, which shows the trade-off between precision and recall. So a high area under the curve represents both high recall and high precision. And a high precision relates to a low false positive rate, and a high recall relates to a low false negative rate. And the third metric shown is the ROC curve, which shows the performance of a classification model at all classification thresholds. So the function compute_metrics takes the following keyword arguments. It takes the data loader object of the validation data, which we defined before, the inference function, which is the loaded inference function, which allows to run the inference process on larger images. So on larger images, then only the 256 times 256 pixel sized windows, and the thresholds water, so the classification threshold defined for water. And this is what we do here. So we first get the inference function. We also define the data loader for the validation subset, and we define here the threshold for water. And then we can compute the 3 metrics, and we can use the function metrics.plot_metrics to plot also the 3 metrics. And this is what we see here. So this is the confusion matrix, which showcase on the rows the predicted classes and on the columns the actual classes, and also the labels land, water, and cloud. And at the same time also the precision recall curve and also the ROC curve. And then as an additional performance evaluation, we can calculate for each of the validation data files the following metrics. So we can calculate recall per class, which is the number of correctly classified pixels divided by the number of classified pixels that should have been returned, and the intersection of union, which is the overlap divided by union. So if the prediction is 100%, IOU is 1. And this means the lower the IOU, the worse the prediction result. And this is what the code below does. So it results in a table with 6 rows indicating the number of validation files and 6 columns indicating the 6 calculated metrics. So for each of the classes, land, water, and cloud, the recall and also the intersection of union is calculated or computed. And then as an additional step, if you trained a model, you might be interested also in saving the pre-trained model. And if you want to do so, you can use the function atomic_save from the PyTorch Lightning library, which saves the model itself. And the function save_JSON from the ML4Floods library allows you to also additionally save the configuration file of the model, which might be good if you want to reuse the pre-trained model and better understand under what conditions the model has been pre-trained. And now we are at the end of the first notebook of the ML4Floods project. So we introduced you to the training process and showed you how you can train a flood extent segmentation model with the help of the ML4Floods Python package and the World Floods benchmark dataset.